Today, we want to talk about complex numbers, and it's going to seem like a really weird shift from talking about vectors, which seems super practical, to complex numbers, which we have given half of a complex number over to what we call imaginary numbers, which is really kind of a mistake on our parts. I don't know if that was a good choice on our part. I wasn't there, so I missed that meeting. But I got back the next day and like, are you guys seriously going to call it imaginary numbers? And everybody's like, I'm sure it'll be fine. I'm like, well, I was still talking about this pi equals, shouldn't we use the radius for pi instead of the diameter? And they're like, no, it'll be fine. It's just dividing by 2, because back then we didn't realize how much people are not going to want to like fractions. So there's that. Anyway, let's talk about complex numbers. Complex numbers are important. They're in part imaginary numbers. So we have to think about some square roots. When we first talk about square roots, we know that the square root of 4, let's use the square root of 9, because I can easily turn a 4 into a 9. The square root of 9 is equal to 3, since 3 squared is equal to 9. So a square root is kind of undoing a square. This is cool because this ancient square root technology can be upgraded to exponent technology. So we can think of the square root of 9 as 9 to the 1/2 power, because then these things will cancel out, right? So think of square roots as 1/2 powers. That'll be important later on. And then when we're learning about these square roots, this is the first thing we encounter. We encounter these square roots because kids are looking at their calculators and say, hey, what's this weird looking button? And the teacher's like, oh, that's the radical button. And the kids are like, oh, well, what's so radical about it? Kids in the 80s were extra weirded out by this button because it was being called radical, and that meant something different to us. But they had this radical symbol, and they go, well, what if we do like something like the square roots of -9? And then we're like, oh, you can't do that. It's not a real number. We didn't say that you can't do that there's no such thing as the square root of -9. We said it's not a real number. And that's really weird at the time you encounter this idea. We say the square root of 9 is not a real number. But the only numbers that you've encountered at this point in your mathematical career are real numbers. That encompasses all the numbers that you've heard about. But yet there it is. Square root of 9 is not a real number. This raises the question, well, what's a not real number? What do you mean by that? Usually the response is from teachers, so quiet you, you'll learn about it later. So this raises the question, what's not a real number? Then we come across the quadratic formula, and there's a lot of square roots going on and a lot of parabolas that don't have x-intercepts. And so we're like, all right, it's time for you to know what these not real numbers are. And so we introduce this new number called I. How do you spell imaginary? Hang on. Go somewhere there's a spell check. It's a gin and an airy. All right, I didn't get spell correct. Thank you. Imaginary. It's a gin and an airy. So I just got to remember martini. That's shaken, not stirred. So gin and airy. And we called it I. And we said I is the number that is the square root of -1. That is, I squared is the number such that when you square it, or sorry, I is the number such that when you square it, you get -1. No real number can do this, because if you square a real number, you automatically have the same sign, a positive times a positive or a negative times a negative. No real number has this property. Because if I take 3 squared, I get 9, because it's 3 times 3. And -3 squared is a -3 times another -3, and that's a positive 9. When you square something has the same sign, you get positive. So I is this imaginary unit. We say, if you square this number, comes out negative. And everybody's like, well, that's not a real number. And so we just went with the opposite of real and said it's an imaginary number. So now, if I want to find the square root of -9, I just break this up into the square root of 9 times the square root of -1, the square root of 9 being 3, and the square root of -1 being I. So we can say that the square root of -9 is 3i. Because if we take 3i and square it, three squared is 9, and I squared is I squared. And I squared is this weird imaginary unit such that when you square it, you get -1. This told us something about all those parabolas whose vertex was above the x-axis and opened upward, that didn't have any x-intercepts, or the vertex was below the x-axis and the parabola opened downward. We found out that all those parabolas still had 2 zeros, they just weren't real. The interesting part is that they were always complex conjugates of each other. I haven't talked about complex numbers, but you can see that's coming. So we invented this imaginary unit. I is the square root of -1. We, like I was there. I missed that meeting too. You'll soon get the impression that I miss a lot of meetings, but that's only because they're meetings. If they had printed an agenda with action items, I would have been there. Sometimes. So we invented this number called I, and it's going to be the square root of -1. And it's going to help us solve some equations that we couldn't solve before. So for example, if we have the equation x squared plus 9 equals 0, we know this equation has no real solutions. But we do have 2 complex solutions. So x squared is equal to -9. And so x is equal to the square root of -9. But since we're solving an equation, we want to make sure we get all of them. So plus or minus the square root of -9. And the square root of -9 is 3i. 3i squared is equal to -9. -3i squared is also equal to -9. So at this point, you're like, oh, dude, you kept calling I the imaginary unit, and now you're talking about complex solutions. So what's this complex number business? a complex number. I spelled P wrong. Complicate things. Has the form A plus B times I. A is the real part, and B is the imaginary part. A is called the real part, and B is called the imaginary part. If A is equal to 0, then our number is pure imaginary. If B is equal to 0, then our number is real. So in this sense, the complex numbers is a superset of the real numbers. All real numbers are complex numbers with an imaginary part equal to 0. So in our sets of numbers, if here we have all the complex numbers, the real numbers are a subset of the complex numbers. Real numbers are complex numbers with an imaginary part equal to 0. So we were learning about complex numbers all along. So now we're solving quadratic equations that have real and imaginary parts in their solution. So let's say x squared minus 4x plus 13 equals 0. Otherwise known as x minus 2 squared, that's going to be a plus 4 plus 9 equals 0 by completing the square. So our solutions x will be 2 plus or minus the square root of -9. And the square root of -9 is 3i. So 2, I spelled 2 wrong. 2 plus or minus 3i. So our quadratic had two complex solutions, 2 plus 3i and 2 minus 3i. Fun fact about quadratic functions: if there are complex zeros to a quadratic function, they will always be in conjugate pairs if the quadratic has real coefficients. So they'll always be in conjugate pairs. It's okay, bud. I know, I said quadratic and then I wrote polynomial. I will, I'll let them know. Yeah, okay. So Colson wants you to know that even though I said the complex zeros of a polynomial with real coefficients, quadratic polynomials, the x squared, that's where if we have a polynomial with real coefficients, it's some quadratic factor that's always going to give you these conjugate pairs. If 2 plus or minus 3i are zeros of some higher degree polynomial, then x squared minus 4x plus 13 is most definitely a factor of that polynomial. So, will that do, bud? Colson says that okay. But the mailman's going to be on the other side of the street, so he's going to get another barking. So we have these complex numbers. And it raises a question. It's like, well, what are we going to do with these complex numbers? We've already admitted that the numbers weren't real, at which point we're just playing semantics. Don't focus on what we called the things in our ignorance as humans, trying to come up with names for the things that we're talking about. Because we need to recognize that our spoken language is always going to be insufficient for communicating these mathematical ideas. Math is just a better language. Every time we try to communicate it in some other language, it just loses something. And math is just disappointed at all these languages' incompetence at expressing these ideas. I'm not even picking on just English specifically, because English has trouble expressing its own ideas. So, all right, let's talk about complex numbers. Let me pause for 1 second. So that is a great question. The great question, odd roots of -1 is equal to -1, right? That is true. So -1 to the 1/6 is I because -1/2. Can we do anything further than -1 to the 1/4 or -1 to the 1/8? We can, which is where this is headed and why we need trig before we start discussing this idea. So that is a great question. That's exactly on point with where we're headed with this. All right, let's think about, so we've got these complex numbers, and we need to be able to operate on these complex numbers. They need to make sense in some fashion as numbers. So let's do some operations. Let's suppose I got some operations like 2 plus 3i. Here's one of these complex numbers. Let's suppose I wanted to take the number 2 plus 3i, and I wanted to subtract the complex number 5 minus 7i. I don't have to tell you how this works. We already know how this works. We only add things that are the same, and when we add them, it doesn't change what they are. So we add the real parts. 2 minus 5 is -3, and 3 minus a -7 is 10. The -3 is the real part, the 10 is the imaginary part, I don't add those because they're not the same. Real parts and imaginary parts, separate parts. In the same way that $3 plus 10 pencils is not 7 of anything. In the same way that -3 plus 10x is simplified. There are extra things that we have to think about. Because remember, in these complex numbers, I squared is equal to -1. So if I wanted to multiply, let's say 2 plus 3i times 1 plus 7i, I don't have to tell you how to multiply these. You already know how to multiply these. Multiplication and addition combine with distribution. Multiplication distributes over addition. So we know to multiply each digit of one number by every digit of the other. Excuse me, each term of one polynomial by every term of the other polynomial. Excuse me, each term in one complex number by every term in the other complex number. 2 times 1 is 2. 2 times 7i is plus 14i. 3i times 1 is plus 3i. And 3i times 7i is plus 21i squared. Now we got to remember to add things that are the same. 14i and 3i are like terms. Oh, and we have to remember that these are complex numbers, so I squared is equal to -1. So this plus 21 is actually -21, or plus 21i squared is -21. So we get -19 plus 17i. I don't have to tell you how to multiply complex numbers because you already know how to multiply when plus is involved. If I raise a complex number to an exponent, I don't have to tell you how to square a complex number because you know how to square numbers. You multiply them by themselves. So we get 1 plus 7i plus another 7i plus 49i squared. We've got like terms with these I terms. Plus 49i squared is minus 49. So we'll get -48 plus 14i. Don't have to tell you how to square complex numbers. You already know. I will admit that dividing complex numbers is a little bit more strange. Mostly because I don't focus so much on rationalizing square roots, maybe than I should. But dividing complex numbers is a little bit different. Let's suppose I have, let's say.
One quick question.
Oh, yes, go ahead.
49i squared became -49? Is that what did you do for that? I didn't.
I squared is equal to -1. That's the thing to remember. I squared is -1. So that shows up there and then down here.
Oh, okay. So it's just 49i squared is just -49.
Yeah.
Okay, got it.
So if we want to, let's say, divide some complex numbers, like -19 plus 17i. Let's suppose I wanted this divided by, I'm just going to write it up and down, in which case I wouldn't need the parentheses, but I will in a second anyway, so I'll just put them there. If we want to divide complex numbers, we have to rationalize the denominator. So where this comes from, it's going to seem kind of weird, but it's going to rationalize, we're going to rationalize the denominator. just like we would with radicals. So that means we're going to multiply the top and bottom by the conjugate of the denominator. It just sounds so funky when I say it, but we'll see why in a minute. So we're going to multiply, we're going to rationalize the denominator. So we're going to have to multiply by the conjugate of the denominator. Now I can't just do the denominator. I can only multiply by 1 without changing the value. So great trick of mathematics, multiply by 1. The other one being add 0, and then after that, change your variables. The reason that we multiply by the conjugate is that this will cancel out the I terms and we'll just have a real number down there. But after that, it's just multiplication. 2 times 2 is going to be 4 minus 6i plus 6i minus 9i squared. So what happens in the denominator is that it becomes a real number. Negative 6i plus 6i cancels out. Negative 9i squared is going to be plus 9. 4 plus 9 is 13. Multiplying a complex number by its conjugate results in a real number. So you multiply a complex by a conjugate, you get a real number. So an a plus bi times a minus bi. You just make the imaginary part the opposite. Still got to multiply the numerator. 2 negative 19s is a negative 38. And then 3 19s is 60 negative 3, 57. So plus 57i. Check my math. It's always very fishy. 2 17s is 2014. And 3 17s is 51. That one's just for some reason one that I know. (38), 60 negative 3, 2014, 30 21. Okay, so I think I'm good. We've got like terms. 57 and 34 is 80 11, so 91i. And negative 38 and 51i squared is plus 51. So 51 minus 38 is 13. 7, how much? 38 minus 50, 51 minus 38. How much is that? Oh my God, I'm looking around for my calculator to do 51 minus 38. The horrible part is I was expecting it to be 13, and the first time I did 51 minus 38, I didn't get 13 because I didn't read 11 minus 8. I read something else, and all of a sudden I'm like, well, hang on, where did I make a mistake? And then I was trying to think about that. Meanwhile, the whole time it was 13 all along. Oh well. Now notice that I got 13 plus 91i divided by 13, and conveniently 13 divided by 13, I can use the distributive property, and 13 divided by 13 is 1, and 91 divided by 13 is 7. Notice that when we did negative 19 plus 17i and divided by 2 plus 3i, I ended up with 1 plus 7i. And it's really good that we got that, because 2 plus 3i times 1 plus 7i is negative 19 plus 17i. That's what we did up here. That's why I chose to start here and just divide by one of these. Clearly, I should have picked the 1 plus 7i. I wouldn't have had this 13 problem, but there it is. Spoiler alert, I would have traded my 13 problem for a 26 problem, and the same thing would have happened. So the good news is we already know how to perform operations on complex numbers because we know how to multiply. Because we took our concept of multiplication of just numbers base 10 like we normally write them, and we applied it to polynomials. And now we're just throwing in this extra bit from complex numbers that I squared is equal to -1. And we end up with just real and imaginary parts. Any questions?
I squared equaling -1 is a constant, correct?
That's just how we define I. That's a property of the imaginary unit.
Okay, so it's constantly like that. It's not
Yeah,
changing.
it's always like that.
Okay. And equations like this will always have I. It won't be some other like letter like X or.
If we're talking about complex numbers, then the I is just is a number now.
I is a number. It's not
If I is a number, it's like 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then I is part of that. It doesn't fall in that list. It's just a number. It's not a variable. It's the square root of -1.
Oh, okay, got it. Okay.
If I replaced it with an X, and then I'm doing something completely different where X is a variable and I'm talking about polynomials. I know this looks like we're talking about polynomials, but these are not polynomials. They're complex numbers.
Okay.
If you're like, oh, dude, they look like polynomials, you are correct, because we're applying the same kinds of things, the same kind of processes to these complex numbers that we did to polynomials. Secretly, we're always doing this, even when I just say what's 23 times 17. Any questions? All right, so what does it have to do with vectors? This seems like a really big shift from vectors, dude. What's going on? So the similarity to vectors comes in how we're going to visualize some complex numbers. Here's what we're going to do. Now, remember, when I write the number 1 plus 7i, or 2 plus 3i, or 2 minus 3i, that's a number. It's just a number. Just like 15 is a number, just like -pi is a number. These are just numbers that have two components. If you think it's weird for a number to have two components, 2/3 of you do not like thinking of numbers with two components, like 2/3. Fractions have two components. Maybe this is why we don't like them in the first place. We think numbers should have one thing. But like the number 23 has two components, a tens digit and a ones digit. Why are we so freaked out? It's because we could see the separation, I think. Anyway, there's a great sketch from Abbott and Costello. I don't know if anybody know who Abbott and Costello is, but it's a math thing. And the joke is that Costello convinces his landlord that 7 times 13 is equal to 28. And he does it in 3 different ways, which are all the same way. He makes the exact same mistake in all 3. And that's what's funny about it. He gives his landlord 3 copies of the same mistake. And that wins. It's like a preponderance of the evidence. The evidence is unconvincing, but if you have a lot of it, people will buy right into it. You know what I mean? So anyway, I don't know what made me think of that. Oh yeah, the digits thing, right? So this number 2 plus 3i is a number. It has two parts to it, the real part and the imaginary part. The sneaky thing is it's not really like the fraction 2/3, because the 2 and the 1/3, those are both real numbers that we're combining. So that 2/3 sits on the real number line. What we have to do to visualize imaginary numbers is say, okay, this is the number line where we find all of the real numbers. And then we're going to put another number line and that's where we're going to put the imaginary numbers. So we're going to think of these numbers with two parts, two components, a real component and an imaginary component. So the number 2 plus 3i will have a real component of 2. And that's not going to fit. It'll be fine. A real component of 2 and an imaginary component of 3. And we will plot that here. 2 plus 3i. It's got that real component of 2 and an imaginary component of 3. And we just think about that as that point in space. So now it's super different from all of our real numbers. It has two components and we visualize it in a two-dimensional plane. Any questions? So the complex conjugate of this number was 2 minus 3i. I have to pick that one because it's the only one of the ones that I've written down that will fit. But down here, if I go to -3, I can plot the point 2 minus 3i. I spelled 2 wrong. Any questions? So we're looking at these complex numbers sitting in this plane, in the complex plane. And then we start to get suspicious because we're in a math class and we had just started talking about vectors and breaking vectors into components. And so we might start worrying that I'm going to suddenly ask you for a different description of this number 2 plus 3i by saying, how far is it from the origin and at what angle does it make with the real axis, the positive real axis? So you're like, well, at least we've done this problem before in the context of vectors. The magnitude of this vector 2 plus 3i, oh, I'm sorry, the distance it is from the origin, is just going to be the square roots of 2 squared and 3 squared. So 4 and 9, 13. That's something that came up with a 2 and a 3i. So the radius is just the square root of 13. And the theta is just going to be the tangent inverse of opposites over hypotenuse, or sorry, over adjacent in the first quadrant. So I have to do it weirdo order because so 3 divided by 2 is 1.5. And then I want the tangent inverse. So I want second tangent inverse, 56.3 degrees. So we got these two different ways of describing this complex number 2 plus 3i. It's 2 plus 3i in Cartesian coordinates or rectangular coordinates. And it's at square root of 13 and 56.3 degrees in polar coordinates. Any questions? All right, that's cool. That's cool. Any questions, comments, deep thoughts? I'll post the notes afterwards. So let's take a look at some things. So recall that negative 9, or 9 has two square roots. Also note that negative 9 has two square roots. In this case, we have two real, 9 has two real square roots. Negative 9 has two imaginary square roots. Both have two complex square roots. So the 9 has two real square roots. Negative 9 has two complex square roots. Or sorry, imaginary. Both have two complex square roots. Nine and negative 9 both have two complex square roots. All real numbers are also complex numbers. All imaginary numbers are also complex numbers. Real numbers have an imaginary part of 0. Imaginary numbers have a real part of 0. This is because all numbers have two complex square roots. Let's plot them. So if we draw our complex plane, we look at 3 plus or minus. I did these wrong. I wanted plus or minus 3. If we look at these numbers, 3 and -3, as the square roots of 9, I've got a 3 up here, which are a real 3, and are, for some reason, I'm putting it 2.5. Okay, that's a weird scale to use. So there are our square roots of 9. Our imaginary roots are at 3i and -3i. Or sorry, our roots of -9 are imaginary at 3i and -3i. So here's what we want to think about next. We know certain things like cube roots, for one thing, respect negative numbers. I just want you to see the form of where these points are, or where these numbers are. There's 3 plus 0i, -3 plus 0i, 0 plus 3i, 0 minus 3i. So here's the thing that we might remember. The cube root of 8 is equal to 2. So the cube root of 8 has one real, the 8 has one real cube root. And the cube root of -8 is -2. I usually phrase this by saying that odd roots respect negatives. And respecting negatives keeps it real. So we'll say 8 has one real cube root. -8 has one real cube root. -8, thanks. Let's look at the number 1. Let's come at this from the other direction. I'm just going to leave this here for now with this suspicious space under the one real cube root part in both cases, although you won't be able to see the space down here because I'm not writing anything underneath it directly. So we know that I squared is equal to -1. What does that mean I to the 4th is equal to? What's I to the 4th power? Well, it's going to be an I squared times I squared. That's going to be a -1 times -1. That's going to be 1. Also, if I take -1 and raise it to the 4th power, we know what's going to happen here. We'll just kind of put 4 copies of -1, and we're going to come up with 1. We also know that 1 to the 4th is 1. And I want to put another one out here. Give you a second to think about what it might be. Negative I to the fourth power is also equal to 1. So we see that the number 1 has 4 fourth roots, 2 real, 2 imaginary, so 4 complex fourth roots. The number 1 has 4 complex fourth roots. Here are 4 numbers. When we raise them to the fourth power, we get 1. Plus or minus 1, plus or minus I. Four different fourth roots. 2 of them happen to be real. 2 of them are pure imaginary, but there are 4 complex roots. Any questions? Here's what we're wondering about. So we have 4 complex fourth roots. Back with square roots, we always had 2 complex square roots. Then with this odd one, we had 1 real cube root. Here's the part that I didn't mention before. The number 8 has 1 real cube root and 2 complex cube roots. Or 2 additional complex cube roots. So 8 has 3 complex cube roots. 1 real and 2 are going to involve imaginary numbers. Negative 8 has 3 complex cube roots. When we upgrade to looking at the complex numbers, whatever root we're taking, that's how many we're going to find. Square roots, 2 of them. Cube roots, 3 of them. Fourth roots, 4 of them. Fifth roots, 5 of them. Let's draw these 4 complex roots of 1. Ooh, I did not give myself enough space. The 4 complex roots of 1, if I plot them on the real or on the complex plane, are at 1, negative 1, I, and negative I. Notice how the fourth roots are spread out. What we want to notice is that the fourth roots are all 90 degrees apart. Go back to our square roots. Our square roots of 9 were 3 and -3. Our square roots of -9 were 3i and -3i. Notice 180 degrees apart. One of my cube roots of 8 is at 2. How far apart are my cube roots going to be? You have no context for this? Just some leading questions by the prosecution? Square roots are 180 apart. Cube roots, or sorry, fourth roots are 90 apart. How far apart are the cube roots going to be? Close. 60, 60, and 60 is only going to get us to 180. 120, 120, and 120 will get us to 360. So the other cube roots will be in the complex plane, and they will all be 120 degrees apart. And the distance from the origin will be 2. And we can figure out what these angles are going to be. That means we can also figure out if we have a fifth root, we should have, if we have, like, say, the fifth root of 32, there should be 5 of them, and 360 divided by 5, they'll be 72 degrees apart. This is one of my favorite things to look at in trig. How organized the complex numbers are, how they're all evenly spaced. So what our task now is, what are these numbers? And if I cube it, do I end up with 8? What's that complex number? And do we get 8 when we cube it? And now we're back, all the way back to that know your values quiz. Our reference angle is 60 degrees. Cosine of 60 is 1/2. Sine of 60 is √3/2. I'll multiply those by 2. 2 times the cosine of 60 is 1. 2 times √3/2 is √3. So it looks like the coordinates are going to be -1 on the x and positive √3 on the y. All we have to do is take -1 plus the cube root of 3 times I and cube it. If that comes out to 2, then I think we're really on to something. Man, if I check that right now, then all this complex number business will become perfectly clear, and you'll totally understand all of trigonometry and all the other math that's gone before. All I have to do is verify that that complex number is -1 plus I times the square root of 3, then cube it to show you that it works out to 8, and then you'll understand everything. It's like plugging you into the matrix. You'll have perfect understanding. So let's do that. Darn it, look at the time. I guess we'll have to wait until Thursday and struggle for with math the rest of our lives. Bummer. All right, that's going to do it for today. I'll see y'all on Thursday. Everybody have a good couple of days, and thanks for playing.